The Artemis 1 mission illustrates some concepts from orbital mechanics. This includes the distant retrograde orbit that it uses, and also provides an opportunity to study how to change between orbits efficiently. This includes the surprising result that to speed up and escape orbit from a planet, sometimes it's most efficient to first slow down and hurtle in towards that planet by firing reverse thrusters instead of just blasting directly forward.
There's a lot of jargon that gets thrown around when people talk about this mission and any other for that matter. So I thought I'd actually talk a little bit about the Oberth effect and gravity assist, slingshots and those kind of things. Actually, all those things are involved in this mission. It wasn't obvious at first until you started looking at what they really did. Artemis 1, that's the Space Launch System as the rocket, Orion as the capsule. It's basically a big test. This 25-day mission, no crew, orbiting the moon, returning tomorrow. And along the way, they deployed 10 small satellites. We've shown some of this stuff before, so I'm not going to spend too much time on it. But on the left-hand side here, you see what the rocket looks like with, this is the whole thing, what it looks like when it's going up. It's got the solid boosters before they drop off. It's got up in the upper stages, it has the Orion capsule, which really includes two parts. There's the capsule itself, that's the only part that actually gets returned to Earth. And then there's the service module, which is put together by the European Space Agency. And that contains propulsion and life support. So that gets jettisoned right before they finally re-enter the atmosphere. They jettison even most of their life support because it's a very short ride down at that point. Very terrifying ride, but very short. So one thing you don't see is what connects the Orion capsule to the rest of the SLS rocket. In between, there is a thing called the interim cryogenic propulsion stage. It's basically an upper stage. It actually provides a lot of propulsion once you get out of low Earth orbit. And then it gets abandoned and actually it gets shot off into an orbit around the sun at the very end of it. So this is that picture. This is taken from Orion. That did set a record. The Orion has gone the farthest from Earth for any human-rated craft so far. It went about 270,000 miles out. That's on the far side of the moon. The Earth, moon is on the other side of the moon, way past that. The previous record was 248,000. So it did beat it, not massively, but it definitely did beat it. The orbits that they're in, the one main orbit around the moon that was used here is called a distant retrograde orbit, which an awful lot of people hadn't heard of, until this particular mission. The distant part means that it really goes far away from the moon, but how far? It's far enough that it goes beyond the Lagrange points with the Earth moon. And what that means is those are points where force is basically balanced between Earth and the moon. And there's a couple of those. There's one in between the moon and Earth and one on the other side of the moon. As long as it basically goes outside of those, it turns out that makes it very, very stable because that orbit is really influenced by both the Earth and the moon. So it's a very, very stable orbit. Now, this would have been used in the past. An earlier version of the Space Launch System, originally under the Obama administration, it was going to go and capture an asteroid and bring it back. And they needed a place to put it. So they're going to put it in an orbit around the moon, which sounds like a pretty dangerous thing. If you screw it up, a big asteroid crashed into Earth. But anyway, obviously, one, that didn't happen. But two, this would have been a very stable orbit to put it in. It does change slowly over time, but it's very, very stable, much more so than almost any other orbit. And that's why they used it. One of the reasons they used it in this mission is that if anything did get screwed up and you had a time to fix it, some kind of loading software or something, because it would go around in the same orbit, you had several shots to fix it quick. So that's one of the reasons they favored that. So it would have been used back in capturing an asteroid, but that didn't happen. The actual first use of it was by the Chinese. They had a lunar orbiter, and they put one in it, and that was only the beginning of this year, so it wasn't even that long ago. The theory behind it had been developed years and years ago. Everybody knew about it, but nobody had ever actually done one, and now they have done one. So it's called a distant retrograde orbit. We talked about the distant part. The retrograde, that's a word that's used in astronomy, rocketry, and it depends completely on context what that actually means. If you're talking about an object by itself, like a rocket or a satellite, retrograde, if you would do a retrograde burn, meaning you burn some fuel to change your orbit, that means it's just in the opposite direction. It has retro rockets and all that. It just means you're going this way so that at least the main component of your thrust is in the opposite direction of what you're going. So that's one use of retrograde. Another one, though, if you're talking about an object around the planet, then retrograde orbit is in the opposite direction of the planet's spin. So, for instance, if you're launching a satellite, you care about whether it's a retrograde or prograde, the opposite, because you got the Earth's spin working for you. And if you launch, especially the closer you are to the equator, if you launch at the equator,
By the Earth's spin, you're already moving about 1,000 miles per hour. That gives you a lot of kinetic energy. You want to add to that speed by launching to the east, the prograde direction, not the other way, which would be the retrograde direction. If you're launching to a polar orbit, one that is passing over the poles, then that wouldn't be a benefit. But the point is, launching in the prograde or retrograde action has a big impact on the cost to orbit for many launches.
But now there's another case where you're talking about a planet and a moon, and you're looking at that combination system.
Then, if you talk about an object orbiting the moon, then the orbit is a retrograde if it spins in the opposite direction of the moon's orbit around the Earth. That's clearest when the object orbit is in the same plane as the moon's orbit around the Earth. Then, from where you're standing, if the moon rotates counterclockwise around the Earth, then a retrograde moon orbit would rotate clockwise. In this diagram of the overall Artemis mission, the moon is orbiting the Earth in a counterclockwise direction. The gray circle to the right, around the moon, is the distant retrograde orbit. The Orion capsule enters that orbit at the point marked number 10. It enters that orbit going clockwise. It only goes half an orbit to point 12 where it leaves that orbit, but without the burn at point 12, it would continue orbiting in the gray circle for a long time. Let's talk about the overall mission. The rocket was launched, and the outbound path is shown in green here. The solid rocket boosters and then the core main stage all dropped off. The interim cryogenic propulsion stage, the ICPS, it did a burn to head for the moon at point 5. After that, the mission split in two. Orion ejected from the ICPS and coasted towards the moon. The ICPS dropped off the 10 secondary satellites at various positions, shown as A, B, C on this diagram, and they also coasted toward the moon. And as both the Orion and the ICPS coasted toward the moon, they slowed down due to the constant pull of Earth's gravity. That's just like throwing a stone up in the air. The stone slows down while it's rising. As both craft approached the moon, however, they also got pulled more by the moon's gravity. We'll cover the details later. That's where we're getting into the Oberth effect and in gravity assists. In general, the idea was to get Orion into the distant retrograde orbit, which is the gray circle. The goal for the ICPS was disposal, just get it out of the way by putting it into an orbit around the sun, escaping the gravity of both the Earth and the moon. Some of the small satellites were also headed for solar orbit. Others were headed for lunar orbits or lunar landing. They generally had their own power, so they could control their own path. Orion's maneuvers near the moon relied heavily on the Oberth effect.
The basic idea is you're changing orbits. You're going from one to another. It turns out there's a question to ask. When should I use the thrusters on my rocket? When should I burn? Do I do it when I'm up high? Well, it turns out you want to do it as close to the moon as you possibly can. You actually get a bigger kick that way, which is not really completely intuitive until you look at it more carefully. And the reason is it really all comes down to that graph right here, which I'll explain in a second.
Basically, it's all related to kinetic energy. Kinetic energy is the energy associated with motion. Kinetic energy increases with faster motion and with heavier mass. It is proportional to the mass and proportional to the square of the velocity. So for a given mass, this graph plots the velocity of an object on the horizontal axis and the kinetic energy on the vertical axis. Now, imagine a rocket is coasting at some velocity v. From this graph, you could read off the kinetic energy. Now, if you burn some fuel for a short time, you would get a burst of thrust, expelling the propellant as gas at high speed. Now, that'll generate a fixed amount of thrust and hence a velocity change of delta v, independent of how fast the rocket is going. The Greek delta symbol in front of the velocity v just means a change in the velocity. So, how much effect does the burst of thrust and delta v have on the kinetic energy? Well, from the graph, you can see the effect of a given delta V on energy, shown as delta E. That same delta V results in a bigger change in energy the faster the rocket is going. It follows from the shape of the curve. The math is shown on the slide. You start off with some initial kinetic energy based on the formula of kinetic energy equaling 1/2 of mass times the velocity squared. After the short burn, the final velocity is v plus delta v, and then the final kinetic energy is shown. You subtract the initial kinetic energy from the final kinetic energy, and there's a term. Now that shows that the final kinetic energy depends on the velocity v, the initial velocity.
The faster you're going, the more energy you pick up. Now, that's different than what's called a slingshot maneuver. That's just based on gravity. You hear that term a lot. And a lot of, awful lot of the interplanetary probes that we've done, where they go from asteroid to planet to asteroid and so on, they all use this. And basically, there, you're just saying, I'm going to go near some object that's moving around the sun really fast. And if I go anywhere near it, I'm going to get kind of pulled along. And the exact effects differ depending on the angle you come in. But fundamentally, you're grabbing, because it's pulling you, you're grabbing away some of that energy. So you get some energy for free. It balances out because you're actually stealing it from the bigger object. But the bigger object is so big, it doesn't notice a difference. You're the small thing like the rocket, and it affects you. So anyway, now this interim cryogenic propulsion system, the upper stage of SLS, uses that in particular, and I'll show you that on the graph when we get to it. But does this really make sense? Most people have trouble kind of getting their head around that because they think, well, okay, we're burning some fuel. There's a certain amount of chemical energy we're getting out of that, and we're using that to blast out the exhaust. How could it possibly make a difference how fast the rocket's going? Well, the way to think about it is, if you are in your rocket, you've got a lot of propellant, which is usually most of the weight of the rocket. That propellant itself has kinetic energy. It's moving along with you. So you're starting off, your initial condition, you're moving along. You've got a bunch of fuel that has its own kinetic energy as well as the chemical energy. When you blow it out the back, then what happens is some of that energy is obviously taken away. The question is how much of that actually transfers to the rocket. And that's where the whole thing is. So think of in some extreme cases. I mean, for instance, if you're sitting on the launch pad and your rocket is just running its engines, but maybe it's still held down by some straps or something. Basically, none of that energy of that burn goes into raising. It doesn't change the velocity of the rocket at all. So that's one extreme case. The other extreme case is suppose you're going along, and the easiest way to think about a lot of these kind of issues with rocket thrust is don't think of it as shooting out gas. Think of it as shooting out marbles. Those marbles have velocity. They had energy. Some of them got dropped off. And if you actually drop them off at exactly the speed you're going, those marbles end up sitting there at zero speed and the rocket goes on. Well, energy is always conserved. So if there's no more energy at zero velocity, there's no kinetic energy in those balls. There are transferred to the rocket. And that's why the whole thing works. So where does this get used in Artemis? It's a multiple place. Let's just follow the path of Artemis. It's launched from the Earth. It's going through these green numbers here as if we split off for the small satellites. And actually, let's look at the small satellites first. That one, there's some vinyl burn here. The small satellites get dropped off. And this thing just kind of comes around. And what happens is, during this period, you're just getting further and further away from Earth. So, it's like anything else that's going up, it slows down. So it's slowing down, being pulled constantly by the gravity. Eventually, it gets really close to the moon and it starts to get sucked in, and then it starts to go faster. Now, for this propulsion stage, it doesn't do any additional burn at all. It just gets slung around. That's called the slingshot effect. But for the Orion capsule, they go ahead and they go down and they go charging toward the surface. But then they actually, when they get as close to the moon as they can, then they turn on their thrusters. They burn it really fast, and that shoots them out. Like it shoots them back up here. So that's kind of weird because you're coming along, you're reaching about the point of the orbit. You think you just expend some fuel here to go into this big orbit, but you don't. Actually, it's more efficient to drop down to the moon and pop back up. Anyway, once you're there, you're in this orbit, it's stable. You're already matching the moon in terms of your velocity on the average, it's going around the moon. So it's really obvious here, right? You get to point 12, this point on the map says, okay, we want to go back to Earth. So how do you go back to Earth? You might think you would just blast your way forward and head toward Earth. But no, actually, that is not the most efficient way to do it. The most efficient way is to slow down. So it's very counterintuitive, but you actually slow down at that point. You do a retrograde burn. You actually purposely slow yourself down. Then as a result, you tumble in toward the moon. And of course, you pick up speed when you do that. And you get swung around, and then you apply a burn. When you're in as close to the moon as you can, you blast your way out, and then you're back on your way. So they're really taking advantage of the odd physics, if you will. It's kind of hard to do all this. They have a lot of computer programs to figure it out. They still do a lot of trial and error. But anyway, they come up with these orbits.
So, by looking at the specific example of Artemis 1, I hope the ideas of a distant retrograde orbit and other uses of the word retrograde, the Oberth effect, and gravity assist are clearer.